Hello guys, so in today's video we'll be looking at some examples, or should I say some exercises in complex analysis. In complex analysis 1, should I say beginner complex analysis. So the first question we'll be looking at is, we'll be proving the following properties from the definitions of functions. Now this is very easy to approach. So the first one we'll be looking at will be exponential to the z plus z1 plus z2, which is equal to e raised to the power of z1 multiplied by e raised to the power of z2. Now suppose that alpha is equal to exponential raised to the power of z1, beta is equal to exponential raised to the power of z2, and gamma is equal to exponential raised to the power of z plus z1 plus z2. Now then, by definition of logarithm, now we'll be making use of logarithmic laws and exponential laws also here. So by definition of logarithm, we have that z1 is equal to the log of alpha, then z2 is equal to the log of beta, then z1 plus z2 is equal to the log of gamma. Now this is very easy to approach now. So we see that the log of gamma is equal to z1 plus z2, which is equal to the log of alpha plus the log of beta. So the log of gamma, which is equal to z1 plus z2, is equal to the log of alpha plus log of beta. Now under logarithmic laws, we have that this gives us the log of alpha beta. That is z1 plus z2 is equal to the log of alpha beta. Now we take the exponential, or the exponent, we take the exponential of both sides, meaning what we're doing now is that from this expression we're taking the exponential of both sides. So we have e raised to the power of z1 plus z2 is equal to e raised to the power of log alpha beta. Now we have e raised to the power of z1 plus z2, which is equal to, now in logarithmic and exponential laws, we have that, let me just scribble it here, note that if we have e raised to the power of log x, the answer is just going to be x. So here now we'll have alpha beta. Now we have alpha beta, but remember that alpha is equal to e raised to the power of z1 and beta is equal to e raised to the power of z2. Therefore e raised to the power of z1 plus z2 is equal to e raised to the power of z1 dot e raised to the power of z2, which is also e raised to the power of z1 z2. That's e raised to the power of z1 plus z2. Then as required. Now this is one of the simplest proofs that you will encounter at the beginning of any complex analysis class. So now we move to the second one. Which is very, very easy. Now the next one, which is b. Now we might be asked to show that e raised to the power of z in bracket, closing the bracket, or in parentheses, raised to the power of n is equal to e raised to the power of n z. Now, in as much that n is taken from 1 to 3 to infinity. Now we proceed. Now we let a equal exponential z raised to the power of n, and we let b equal exponential z raised to the power of n for easy focus. Sorry here. We let b equal to exponential n z. Now we assume that a is equal to b by implication, but from the definition of logarithms, and closes in the brackets, we have that a, which is equal to the exponent of z raised to the power of n, is given as log a is equal to log exponent of z raised to the power of n. Now this implies that the log of a is equal to z raised to the power of n. We name this as equation 1. Also b, which is exponent of nz, will be given as the log of b is equal to the log of exponent of nz. Now we'll have the log of b is equal to nz. We'll name this equation 2. Now we have this as equation 1 and we have this as equation 2. What we do now is that take exponent, the exponential, take the exponential of both sides, meaning we are doing log a is equal to z raised to the power of n. This will be log a, and we have exponents, since we're taking the exponential of both sides. So we have exponents. The exponential log a is equal to the exponent of z raised to the power of n. This implies that we have a equal to the exponent of z raised to the power of n. I'll name this a star now. Now, similarly, we also have that log b is equal to nz. Now, since we know log b is equal to nz, we'll take the exponential of both sides. When we take the exponential of both sides, we'll be having the exponent of log b is equal to the exponent of nz. Now, this will give us b is equal to the exponent of nz. We name this double star. Now we can say that. It is obvious that a is equal to b. Hence the exponent of z raised to the power of n is equal to the exponent of nz, which we can also written as z raised to the power of n is equal to e raised to the power of nz for all n is equal to 1, 2, 3. Now, as required, this is very easy and very self-approachable proof for you to show that in an enclosed bracket of e raised to the power of z raised to the power of n is equal to the exponential of nz for all n equals to 1, 2, 3, and so on. Now we move on to the next proof. Let's name this C, where we'll be showing that the sine z plus pi is equal to negative sine z. Now, in this particular question, we'll be taking a brief recap on trigonometric identities. Now, so we can see that from trigonometry identity, we know that the sine of z plus pi is equal to sine z cos pi. So it is very obvious that we can see that if we make use of trig identity, that sine z plus pi is equal to sine z cos pi sine pi cos z. Now we know what cos pi is and sine pi. Then if we put all this together, we'll be having negative sine z. Now since cos pi is equal to negative 1 and sine pi is equal to 0, hence sine z plus pi is equal to negative sine. You can see it's a very easy, very quick method of approach for you to show that sine z plus pi is equal to negative sine z. Now we move to the next one. Where we need to show that e raised to the power of iz is equal to cos z plus I sine z plus I sine z. Now, for us to show that this is equal to this, the left hand side is equal to the right hand side, we will show from Maclaurin's series. From the Maclaurin series expansion of e raised to the power of x, where we know that the Maclaurin series of e raised to the power of x is equal to 1 plus x raised to the power of 2 factorial plus x raised to the power of 3 factorial plus x raised to the power of 5, x raised to the power of 4 factorial plus delta plus x raised to the power of n factorial plus infinity, which is equal to, we now have the finite infinite sum, which is equal to this of x raised to the power of n factorial. Now what will be very easy. Now we put x to equal to I z in this expression. Now we have e raised to the power of I z will be equal to 1 plus I z squared over 2 factorial plus I z cubed 3 factorial plus I z raised to the power of 4 over 4 factorial plus this relation of I z raised to the power of n factorial. Now we have this to be equal to 1 plus I z. If we do this in accordance to complex analysis, if we resolve this, we'll be having negative z squared all over 2 factorial, negative I z cubed all over 3 factorial plus z raised to the power of 4 factorial plus minus sign, sorry, this is a minus sign, so till infinity. Now what we do now is that we group them. We group them up. So now we say e raised to the power of I z is equal to grouping. Now we have 1 minus z squared. Group the one that doesn't have I. That's 2 factorial plus z is about 4 factorial minus infinity. Then plus I. Now we get the i's now. We have z negative z is about 3 factorial. 3 factorial plus z is about 5 factorial. Now, we discovered that from Maclaurin series that this particular expression is given for cos z and this particular expression is given for sine z. Now, since we have both this, what we do now is that hence we can see that e raised to the power of iz is equal to cos z plus I sine z as required. Now we'll be looking at another. Now we'll be looking at showing. I want to show that e raised to the power of z is equal to cos z plus sine z. Now also we approach this from Maclaurin series. So we say from Maclaurin series expansion of e raised to the power of x. So we have that e raised to the power of x, same time from our previous assessment that e raised to the power of x is equal to 1 plus x squared over 2 factorial plus x raised to the power of 3 factorial plus x raised to the power of 4 factorial plus x raised to the power of 5 factorial, and so on it goes, plus x raised to the power of n over n factorial. Now what we do is that we put x to be equal to z. Now putting x to be equal to z, we have e raised to the power of z is equal to, meaning anywhere we see x in this relation above, we make it z. So we have 1 plus z squared over 2 factorial plus z cubed over 3 factorial plus z raised to the power of 4 factorial plus z raised to the power of 5 factorial plus and so on plus z raised to the power of n factorial. Now what we do now is that we group them again. We group them, so we have e raised to the power of z is equal to 1 plus z raised to the power of 2 factorial plus z raised to the power of 4 factorial plus and so on. We close the bracket, then we have plus, open another bracket and say z plus z raised to the power of 3 factorial plus z raised to the power of 5 factorial and so on. Now under Maclaurin series we know, or we have that this particular expression is given as cos and this particular expression here is given as sine z. So hence e raised to the power of z is also equal to cos z plus sine z as required. See, it's very easy to push this. Now I'll be doing the last one now for that one. Let's start it. So the last one now, we have to evaluate the exponent of 1 plus pi r. Now to evaluate this, now what we do now is that we're going to make use of the exponential laws. Now what we know now is that we're going to make this exponent of 1 and the exponent of I pi. Now we say this is equal to the exponent of 1 and this is cos pi plus I sine pi. Since, let me put it here, since the exponential of I pi is equal to cos pi plus I sine pi, we showed in the previous questions. Now the exponent of 1 plus pi I is equal to the exponent of 1 in bracket cos pi plus I sine pi. I sine pi is equal to the exponent of 1 cos pi plus I, the exponent of 1 sine pi. The exponent of 1 sine pi. Now we know that this expression here will give us 0 if you evaluate, and this expression here, since cos pi is equal to negative 1, so we have that. So now we know that we have the exponent of 1 cos pi plus I exponent 1 sine pi. Now we know that sine pi is equal to 0, so this whole expression will be equal to 0. But we know that cos pi is equal to negative 1, so we'll be having the negative exponential of 1. Now the negative exponential, which we know to be negative 2.7182, and so on, which we can also write our answer as negative e as our final answer. So thank you for watching. Please like, share and subscribe. Thank you.